Students are going down, getting to the most fun part of the course. What? Hashem. Well, class is starting. Okay, so this is, I don't need to tell you, this is the last week of the semester. There will be a tutorial today. So we have the regular lecture, 10 to 12, and then at 12 actually we'll complete the discussion about precession, so at least you'll see where things come from, and you see that it's a big hole in your knowledge, which is you feel by that. But then, first thing first, so today we're doing cosmology. My feeling is that we could have finished today, so we have one more lecture on Thursday, which I still have not decided what to teach on Thursday. We'll see how it flows. If you want to continue with cosmology, we can go slightly deeper. If you want, we can do gravitational waves. If you want, we can do some review for the exam. The exam is August 4th, I think you know that. I will not be presently in the exam, but actually I will. We'll talk more about the exam on Thursday. So we're doing cosmology. There are still things that we have not talked about. So cosmology, again, solution to Einstein's equation. It's a symmetric spatial part of the universe, homogeneous and isotropic, end up in the Robertson-Walker metric. E squared is a minus E squared plus A squared of T. ER squared over 1 minus KR squared plus R squared D omega squared. Values of interest of K, minus 1, just an open universe, 0 is a flat universe, plus 1 is a closed universe. A is a scale factor which evolves in time. To that, the way how A evolves in time, for that we plug into Einstein's equation, and we end up with two equations known as the Friedman equation. This is Robertson-Walker metric, and Friedman equations. A dot dot over A is equal to minus 4 by G over 3 rho 3p. Rho is the energy density, P is the pressure, and A dot over A squared is H by G over 3 rho minus K over A squared. And for that we need to add an equation of state which expresses a relation between rho and P. And we show that that depends on the content of the universe, which can be either matter, radiation, or vacuum. So that rho vacuum goes as A to 0, rho matter goes as A to the 3, rho radiation goes as A to the minus. Since the universe expands, that Hubble's told us, that means that A dot is greater than 0. Then we show that in the past, A must have been smaller. Essentially, when A approaches 0, all the coordinates compress into one point, and we call that the Big Bang. This is T. This is T0. This is today. This is A of T. We are here now. A is growing. In the past, it was somewhere here. Apologies. And this is the Big Bang. What the Big Bang is sometime in the past where all the coordinates were multiplied by 0, so they were together. What it is not, it does not mean that the universe started to expand into something else. As I mentioned, the universe can be infinite, and it could have been infinite back then. Simply the density that went to the extreme. the future. That again depends on the content of the universe and on the geometry of the universe. If the universe is flat or open, it will continue to expand forever. If the universe is closed, on the other hand, it will continue to expand slightly and then at a certain point it will go down back. That's called the big crunch. We know today, this is as far as we know, at the best of our knowledge, this is not going to happen. What will happen is that the universe will continue to expand today, even accelerate, because of this dark energy. Then we spoke, I introduced to you the curvature density. Rho C is introduced to be minus 3k over 8 pi g a squared, from which you could write down the second Friedman's equations as 1 or omega c minus k over h a squared, and then 1 is equal to some I omega I. I checked it out in the literature. This is the way it's being Rho C for curvature. So yeah, this is different than the critical density. So critical density, I'll simply write this rho cret. Then we discussed the cosmological redshift. Which essentially we said, okay, we are looking at a distant object, let's say a galaxy, and we see it receding away from us. It is not. It's not moving at all. What changes is the coordinates. This is the coordinates back then. Time evolved in this direction, and this is the coordinates now. Simply, there's a scale factor A of t, which goes. So if I put one galaxy here, same galaxy, another galaxy here, same galaxy. Looks to us as if this galaxy is receding away from us, but it's not. Simply the universe expands. Yeah?
Isn't it like a t plus delta t over a t? Like how much it change the scale?
Yeah, well, let's say this is today, so this will be a t0, a0, which is a t0. This is t1, so a t1. Right. Remember, in cosmology, 0 represents today. Right. And then the co-moving distance, so the distance is not changed, right? Co-moving distance is fixed, but the proper distance changes. So if I write the co-moving distance as L0, then the proper distance is L0 A of t. Right? So if there is a photon that is emerging from this galaxy somewhere here, towards us, it will continue to propagate, eventually it will reach us. Now, right. So what we're going to see. So L of t, this is L of t, L of t proportional to A of t. And so we mistakenly would say that this galaxy is seen to recede away from us at some velocity, delta v, which is d over t of delta L, which is just A dot delta R, or A dot over A delta L. And then if you're looking at the frequency of this radiation, we call it omega, then we'll see a Doppler shift delta omega over omega, which is minus delta V over C, minus A dot over A, delta L over C, minus A dot over A, delta T, or simply minus delta A over A. In other words, omega T times A of T is constant. For omega goes 1 over A. So instead of the frequency, omega 0 over omega 1 is A1 over A0. And so it's custom to define the redshift Z as lambda 0 minus lambda 1 over lambda 1, which is A0 over A1 minus 1. And that is something which we measure. Just a second. There is one important thing to notice. I mean, the whole derivation is done in an identical way to a Doppler shift. But it's not a Doppler shift because galaxies are not moving. So the whole idea of a redshift is the reason why we're seeing this redshift. Right? This is something which we measure. Right? We're seeing emission lines or absorption lines, and we identify the elements from which they come. So we know which frequencies we look at, and we know what the frequencies that we measure, and we're seeing that these are redshifted. But what it really represents is the evolution of the scale factor of the universe from the time they were emitted to today, when we see them. And why is that not a Doppler shift? Because we're seeing the same effect even if the galaxies are not moving. Right? So if the scale factor is a function of time, if t looks something like that, right? And the emission time, this is today, t0, this is t1. Right? We'd still see the same effect, although we're not moving at the time of emission, we're not moving at the time that we observe the photon. Still the same effect is here, because it's got nothing to do with the motion of galaxies.
Where do we observe this?
What do you mean, where do you observe?
Where do we observe galaxies which are not moving relative to us and still have a redshift?
No. I said if A was like.
So this is an assumption.
This is just a demonstration. We will solve today Friedman's equation completely, and you'll see how A really evolves in time. But well, this is to argue that we'll see the same effect even if A was completely flat. Just the difference in A between the observed time and the emitted time.
But we don't have a real observation of a case like that.
No, like that? No. This is what this is. Okay, now there are a few questions. Yes, you first.
Does the expansion affect us in smaller scales?
No. Again. So this is something which is really confusing here, right? Remember, what went into this derivation? What we're doing is exploring the consequences of FRW metric, Friedman-Robertson metric. And this metric is valid only under the certain assumptions, which we stated exactly what they are. In particular, that the universe is homogeneous and isotropic. And as I said, and I'll say it very clearly, this is not valid on a scale of definitely not the solar system, definitely not a galaxy, and not even a cluster of galaxies. Only on a much larger scale. Okay? Because in our solar system, obviously, it's not homogeneous and not isotropic. So we don't really expect to see any effect in the neighborhood of our solar system. In fact, you could try to solve Einstein's equation in our neighborhood. In the solar, if you're just looking at our solar system, of course, the most relevant solution is the Schwarzschild solution. Yes?
Does the gravitational redshift exactly the same way, just different metric, or it's fundamentally different derivation?
The I'm not sure what you mean by different way. Maybe explain yourself.
I'm saying if this the gravitation, quantum gravitation redshift, cosmological redshift, just same phenomenon but different metrics.
No, they are completely different phenomena. Right? The only reason why both use the same redshift is because astronomers, when they look at the telescopes and they see emission lines, identify emission lines, absorption lines, they are seeing them all being redshifted, so shifted towards the red part of the spectrum. That's the only reason. But we're talking about completely different physical phenomena.
You know, I'm saying, is there some root these two phenomena between just especially the same phenomenon with different metrics, or
in principle, are you asking specifically to compare the Friedman-Robertson-Walker metric to the Schwarzschild metric, or are you talking about completely other metrics?
I'm saying comparing this, can the cosmological redshift be thought of as like the gravitational redshift, but with a different metric used to derive the?
No, I don't think so. You can have the gravitational redshift. Again, remember where it came from. Right? In the basic sense, you may be right because it came from a different G mu nu on different locations in space-time. Right? And here too, but this is something which is somewhat different because here we're talking about
Time.
yeah, the fact that the metric here is changing with time. We don't have that in the Schwarzschild metric. Okay, yeah.
So just to see that I understand correctly, the redshift, not the gravitational redshift, this redshift,
Cosmological redshift.
comes from the difference between the coordinate scale at the time of emission and the coordinate scale at the time of absorption.
Exactly.
Now, so it's not a Doppler thing.
It's not a Doppler.
If I would imagine a world with no coordinate change like that, just matter exploding, what would be? I would still have some redshift because.
What do you mean by exploding?
All the matter was concentrated near a point and escaping.
And the metric itself will be fixed in time. So, for example, it would look like that, but without this A, let's say flat universe.
Flat universe, yes. So then I would have a Doppler redshift between.
And yes, you'll have this classical.
What is the observation that tells me that the world that I was suggesting is the wrong one and this one is the correct one?
Well, there are many. There are actually 5 different ones, and we're going to get to them. What's the other place to do?
Becoming faster than the speed of light.
Sorry?
The velocities of becoming faster could be faster than the speed of light. Because it's not really a velocity.
No, the only thing you can get is the redshift. I'm not sure what you mean. You don't get velocities.
No, I mean, in the
You don't get really velocities here. Right?
no, I meant when
The
we
photons
say-
that you're seeing, the photon was emitted, traveled at the speed of light, and we're seeing it today. It still travels at the speed of light. What you may refer to is what happens if you're talking about massive particles. But they will be, actually the calculation for massive particles would look the same. Only what will happen is that you'll see them slowing down. And we can do that, it's quite easy. So if instead of photons, right, there will be a beam of particles, let's say for example cosmic rays, that have a finite velocity, right, v. So again, let's have these 2 separate galaxies. And let's say we want to send, or the guys from the other galaxy want to send a delegation to come and visit us for some reason, right? And then they will build a spaceship that travels at the speed of v, which is of course smaller than the speed of light. and when they cross a proper distance delta L, time delta t, then the velocity of us relative to them will be delta u is a dot over a delta L, which is a dot over a v delta t, which is v delta a over a. So this is the second observer's velocity, relative to the first. And then the observer, the second observer, will see the particles travel as velocity. Second observer will see particles travel at v prime. Now it's just classical velocity addition. Just v minus delta u over 1 minus v delta u. What? Special relativistic, right? So this is approximately v minus 1 minus v squared delta u plus o delta u squared. You can write this v minus 1 minus v squared delta a v delta a over a. Or delta v, which is v prime minus v, is a minus v 1 minus v delta a over a. Or integrating, we get the momentum, which is v over square root of 1 minus v squared. C, of course, is equal to 1. It's just constant divided by a. Pretty straightforward. Which means that the momentum goes 1 over a. If it's not relativistic, then the momentum is equal to the velocity, and then the velocity will go plus 1 over a. Just go over the code.
What did we add to delta L fixed to
And what?
in the first line?
Yeah.
What did we add to delta L fixed to a changing time?
Delta L is v delta t.
Plus a.
No, I have a dot over a, right? This is the velocity, relative velocity. A dot over a times delta L. Think of it a little bit. Okay, and that comes to the next subject, which is one of the most interesting ones. How do we measure distances? Distant galaxies. Parallax, right? You all know what is parallax? Yes, okay. So parallax is good to measure nearby stars. It's not good to measure distant galaxies. They are way, way, way too far. Okay? But there is some, when you think of it, there is something which is even more basic. Right? What is the meaning of a distance to a galaxy in a universe that is constantly expanding? You cannot stop the time. But what does it mean? The distance to a galaxy. There's something which is really basic here. By the time I get there, it will already be.
The more distant they are, the more relative velocity.
In a way, yes. So how do I know what the distance to the galaxy is? I look at the galaxy. Okay, I can see, let's say that I identify the redshift of the galaxy because I look at the lines and I identify the origin of these lines.
Supernova brightness.
Oh, what do you mean by supernova brightness?
All of the universe, they are supernova, and the process is known.
And what?
And the process of collapse into a supernova is known.
Let's say. So.
And at least for some types of supernova.
Yeah.
And the expected emission and expected brightness will depend on the distance.
Now you're talking. Okay. So what you're referring to is what's called standard candles. Right? I'm seeing a light. How do I know if the source of light is very bright but very far, or dim and close by to me? Right? You understand, if I put a 60 watt lamp here, it'll give me some brightness, and if I put a 100 watt over there, I might get the same brightness. Right? So think of the same in terms of stars. Now I'm looking at the star. I can measure the brightness of the star. How do I know if the star is very, very bright and very, very far, or very, very much dimmer but closer by? I would see the same flux. So what I need to know is something which is called standard candles, and you're right about the supernova. I need to know something about the object that, if you tell me, okay, this is a 60 watt lamp, then it's okay, then I can scale it, right? I need to know how much, what is the luminosity? Luminosity is how much energy it emits per unit time. Right? So if I know that, I have no problem. Then I can define what's called as the luminosity distance. Distance measurement. In the universe. So first, there is more than one way to define the distance in an object. I'm going to describe here two. There are more, which I'm not going to describe here. So one way is called the luminosity distance. And that's called dl. And it's defined as dl squared is L over 4 pi f. Or f is L over 4 pi dl squared. So L is the luminosity, is normally in ergs per second. And f is the flux that we're seeing. It's typically ergs per centimeter squared per second. And the idea, as you can see, is very simple. I assume that I have a source of light, which I happen to know its luminosity, and I also assume that it emits spherically, and so isotropically in all directions, and I know what is the flux here. Then I know, assuming it's a flat space, then this would be a force valid, and I can measure the distance. So if I know the luminosity, the flux is what I measure. Then it's fine. Of course, I need to know what is the luminosity, so I need to know what is the standard candle, but as I mentioned, there are ways today to know some objects which we believe we understand them well enough that we know what is the luminosity. It's called the absolute luminosity, to be more precise. But of course, this is completely analog to what happens in flat space, where everything is very simple. Now, if we look at conservation of photons, right, all the photons that are emitted, all directions, eventually we'll have to cross this sphere. Simple conservation of photon number. What is the physical distance of this sphere from the source? V. If we have the coordinate r, then d is a0 r. A0 is the scale factor, right? But that's not enough. Why? Because by the time they reach us, right, they lost energy, photons, right? How much the energy went down? 1 plus 7, right? That's 1. And if we have 2 photons, we're talking about the flux here, right, per second, then the time, right, also increases between these 2 photons by another 1 plus z. Right, so delta t,
1 minus.
right, delta t observed is 1 plus z delta t meet, and frequency, so nu observed is 1 plus z minus 1 nu emit. So overall, what we get is that the observed flux over the luminosity is 1 over 4 pi, and then A0 squared, R squared, 1 plus Z squared. Which means that the luminosity distance is A0 R times 1 plus Z. Okay, so that's good. So this is something which, again, we can measure in principle, the luminosity distance, assuming we know what is the luminosity. Which, we know enough about astronomy, various astronomical objects, that we can have a good idea of what is the luminosity. But we still don't know R. R is a coordinate, which is completely general here. We did not specify. So we can measure D, you can measure Z. These we cannot measure, so we have to be a little bit more careful.
How can we measure?
That's right.
How can we measure?
See? By spectral lines, spectroscopy. During the spectroscopy, I identify hydrogen as specific lines, and I can see them.
So,
And then I compare them to the frequencies that I see.
okay, so then we can see when exactly when it was measured, right?
Nope.
Why not?
If I'm looking at the sun is constantly emitting. The sun, I can assume it's a steady state, a star in a steady state. It continues to emit. It's emitting today the same way it emitted a million years ago. It didn't change. The photons don't tell me when they came, but they were emitted.
Why? Does it tell using Z?
No. Does that tell me where, again, so that tells me the redshift of these photons. DL is the distance. Wait another 10 minutes and I think you get the answer. Okay.
Just A1 times R.
What?
This is just A1 times R.
Yeah, it's A1 time R, but it's not really helpful. Before we're going to talk how we actually measure that, I mentioned there is more than one way of measuring distance. So let's talk about another way, which is called angular distance. That's obviously called dA. Yeah?
When we calculate in Z, we lost the redshift because of gravitation and
You don't calculate, you measure, yes. You have to take this into account.
so how can you measure Z if you don't know the velocity and you don't the process the Doppler shift and you don't know the mass, so you can calculate the gravitational.
Yeah. Life of astronomers are tough. I didn't say it's easy. But seriously, we had these calculations. I think you had these calculations. If you look at the gravitational redshift from the sun, right? We actually did this estimate, and you saw this is a quite small correction. I mean, it's good enough to be detected, but it's not a very big one. Right? This can be orders of magnitude larger. Right? I mean, from the sun, I think, if I remember properly, the numbers were something of the order of 10 to the minus 6. Right? Here we can talk about redshift of 2.
The cosmological shift of the sun.
Not of the sun is 0, right?
Ah.
It's in our universe. But when you're talking about, you're asking about, okay, now I'm saying a photon coming from a distant galaxy. Right? So how do I know? So when I measure the redshift, you're absolutely right. The redshift is I have to compensate both from the cosmological redshift and from the gravitational redshift. But in many cases, we can neglect the gravitational redshift.
Because the time is big enough and aging is fast enough, so
It's simply far enough. It's not changing. Yeah, depends on one step at a time, or will be in time. Angular diameter. What do I mean by angular diameter? The angle in the sky. So let's say I have a galaxy which is not too far away, so I can actually see its size. But I'm here, I'm the observer somewhere here. And I'm looking simultaneously on this galaxy. Of course, it emits 2 photons at the same time, T1, so 1 photon from here, 1 photon from here. So I'm watching this galaxy and I'm seeing it at an angle delta. Now, in fact, this is not a very useful thing because there are only very limited galaxies who can actually do that. Normally they look like dots. I think after all, I'm going to ask you when this is going to be actually quite relevant. But let's say that I'm using delta. And what is D? D is R times A now of T1 times sine delta, but this is approximately delta. Right? Just angles. What?
it's just kind of that parallax. Similar to the parallax calculation.
No, because in parallax I'm changing my location of observers. Right? In the parallax, there is a star on some background stars. I am looking at that star in this direction, and then a year later I'm changing my point of view. And now I'm seeing this star at a different angle relative to other stars. Here, I'm just watching the galaxy, and it's big enough so I can actually measure its size, and it captures some angle delta on the sky, which is obviously typically very, very small.
How do you measure the size? How do you measure the galaxy size other than the angle?
Well, I don't. I'm seeing just the angle. Let's say it has a size d, then the size d is, well, what I'm really seeing are photons coming from this region, from this one side, and from another side.
So in this equation, D is unknown, A is unknown.
Yeah, of course. E is unknown. And the only thing I know is delta. So I can define now, again, if it was known, right, then what would be the angular diameter? dA would be delta was d over dA, angular diameter. So we define dA such that delta is equal to d over dA, again, which is what would be true if we had a flat space. In other words, dA of z, right, is R A T1, which is A0 today, right, times R, this is a T1, times 1 plus Z minus 1. Which means what? What's the relation between DL and dA then? Yeah. So dA for dL is 1 plus Z squared dA. There is no right or wrong here. It's just the way we make the measurement. It's just what we measure. Again, we don't see directly dA or D or dL. We just, what do we see? We see L, we see delta here, and we may hope to see D. Or we don't see D, but we may hope that we have some knowledge of the size of the object. Now, the question, so what objects this could be relevant for?
Relatively small galaxy clusters.
1, yes, but we do have a problem understanding what is the size of this unit t. That's true. First, yes, this is way more in use than this one. There are other ways of measuring. They are less useful because there are not that many objects that we can actually make this measurement. So DL is way more useful than DA. A place where we see it most is when we look at fluctuations on the cosmic microwave background. Okay? Cosmic microwave background is nearly homogeneous, nearly isotropic, but only nearly. There are some fluctuations in there, and these fluctuations tell us a lot. Really. So maybe one option is that we'll dedicate Thursday's lecture to the cosmic microwave background. See what it tells us. Okay, so that's another way of measuring. Now what we want is to take DL or DA, the same, and express them in terms of things we can actually measure. Let's see how we do that. Is that clear? Can you erase that?
What do you mean by R? T1?
A is a scale factor.
No, R.
R is the coordinate.
In the one next to it.
R at T1. Anyway, at T1.
But to
Because
assume
the emission is from here, right? It's emission from here at T1.
To assume it's stationary, it's going.
Right.
Don't to assume the galaxies are stationary.
Yes. Actually, yes, and I don't need this R. Right. Still need to know what
No,
these are.
A,
You're right.
in
A,
A.
yes. A, I don't need. Sorry, A, of course, yes. You're right. I don't need it. Okay. So our goal now is to try to see if we can get an expression for DL which is not involving R, which we cannot measure. And of course we can't do that. So we take this metric, this is Robertson-Walker metric, forget about the angular motion. So we have a 0 equal ds squared is minus dt squared plus a squared over 1 minus k r squared dr squared. So we can move dt to the other side. And then we can integrate integral from t1 to t0 of dt over a of t is integral from 0 to r1 of dr over 1 minus k r squared to the power 1 half. Right? Everything here is legal. But this is something which you can solve immediately, actually. If k is equal to 0, what? Just r, right? R1 here, right? So R1 for k equal to 0, right? If k is a 1 plus 1, arc sine, sine minus 1 of R1. And if k is equal to minus 1, then it's arc hyperbolic. That's not bad. Now, if the galaxies are not very far, you can do the usual trick and use a Taylor expansion. So A of T1, you can write it down as A0 plus A dot at 0 times T1 minus T0. Plus 1/2 a dot at 0 times t1 minus t0 squared plus, so Taylor expand. A of t. Yeah?
We had basic problem here. You said that you can take k equal to 1 or minus 1 or 0 only because you can rescale the r coordinate.
Correct.
As you can see. But after rescaling this coordinate, this isn't the actual distance we measure.
we measure D
Yes.
and Z. We don't know what is R. A, actually, we do have a way of knowing. We'll discuss that later. But we don't know what is R. That is my problem. That is why I need to now rederive this equation without R. That's what I'm doing right now. I want to have a way of measuring the distance to a galaxy, knowing what is D, DL or DA, it doesn't matter, because if I measure the redshift is measured, this is measured, this is measured, this I can infer, this I don't know.
My problem is R after extending doesn't have to correspond to actual distance. Distance over K, square of K.
R is a coordinate. I mean, I specified K. K is given to me. Right? I use it once. I use K as known. Once I specify K is 0, I assume it is known, and that's it. I don't. It's not. I don't touch it.
The problem is that in this freedom metric, after scaling R, photons don't have to move at the velocity of 1, c.
Yeah, they do.
Why? We
The
scale
velocity of the photons will be c, regardless of how I scale the coordinates. Right?
we scale the coordinates. Oh.
I measure in centimeters. I rescale c if you want. Right? I can decide on the unit length to be 1 meter. I can decide it to be 1 kilometer. I can decide it to be 1 centimeters. Photons will still travel at the speed of light. Okay?
No, speed of light.
Photons
the
still
difference.
no. Speed of light is the constant. Right? So you can say that I rescale r such that c will always be 1. Okay? And it doesn't matter which unit I'm using. C is always 1 in the natural units.
You say you can't rescale R twice, once to 8K or to 1.
Yeah, I can.
normal.
I can. I showed you actually that. I can show you that because I can rescale R and A. Right? I'm scaling both of them, both R and A. Yeah? Again, R is just is unknown. Right? Because I did not specify what is the unit measure. Right? This is not something which is constant of nature. The things that I can measure for speed of light, which I normalize to 1, Hubble's constant, etc. Redshift is something I measure, D is something I measure. Now let's move on. So I said I'm using Taylor expansion. So I write it as A0 times 1 plus A dot over A. 0 times T1 minus T0 plus 1 half A dot over A. 0, T1 minus T0 squared plus 10. So this is simply A0, 1 plus, what is written here? H0 times T1 minus T0 plus, what is written here? So it's actually minus 1 half Q0, H0 squared. Remember the Q0? Promise you. We're not putting it for nothing, right? T1 minus T0 squared plus whatever. What is the?
How did you apply that by H2 squared?
I just use the definition.
Q defined by A dot over A.
There you go. That was an exact definition of Q and of A. Right. Go back to the definition. H0. H was defined as A dot over A, and Q was defined as minus A dot over A squared. Go back. What we already learned.
We didn't use H.
What?
We didn't use Q too much, so.
But I promised you I'm not defining things for nothing. I don't think there's anything that I'm defining that is not being used. Actually, that is something serious because you see it by now, right? We're close to the end of the semester. It's so easy to get lost here that what I really did was to cut down everything which is not absolutely essential. I deliberately left only the things that are absolutely essential for you to understand. Basically, we can go on. Yeah. There's no limit. Yeah. Okay, move on. Okay, now at small radius, right? Close enough galaxies, all these end up with an R, right? The Taylor expansion on the right-hand side will always give us an R. So we can write down R. It's equal A0 minus 1. Now again, it's 1 over. So I basically Taylor expand the 1 over A here, right? Take that and reverse it, so I get A0, 1 minus H plus whatever. So it's A0 minus 1, now T0 minus T1, plus 1/2 H0, T0 minus T1 squared, plus, that's pretty straightforward to do. I skipped one line of deriving it. Just plug it in here, and then reverse it. Now,
K equals 0.
what? No, because for small r's, this will also give me an r.
Oh, okay. Assuming the R is small.
Yes. I do a Taylor expansion, that means it's not too far. So, not too far galaxies.
How small is that?
6.
How small is that? Well, you see. A dot over A times T1 minus T0 is much smaller than you need. So, you know, A0 times delta T is much smaller. Not too far galaxies. We'll have that. So, now I can again use a Taylor expansion. Here. Take that equation and divide by A0, and I have A over A0, which is simply 1 plus Z. So I have a 1 plus Z is equal 1 plus H0 T1 minus T0 minus 1/2 U0 H0 squared 1 minus T0 squared plus whatever. That's 1 over 1%. Right. A1 over A0 is 1 over 1%. So again, 1 over 1% is approximately 1 minus Z plus Z squared minus whatever. Again, I'm Taylor expanding things here. Put it in here and compare, and you'll end up that T0 minus T1 is 1 over H0 Z minus 1 minus Q0 over 2 Z squared plus extra terms. This is 2 lines from here to here, which I assume you can do it at home. If you absolutely need it, I can do it here, but I don't think you need it. And this we can take and put it in here. This is for T0 minus T1. And we get that R is equal 1 over A0 A0 Z minus 1/2 1 plus Q0 Z squared plus whatever Taylor expansion. What? I just took that T0 minus T1 and put it in here.
We left everything.
I I neglected everything, all the higher order transforms.
Didn't neglect all higher orders of Z.
I did neglect all terms of Z which is greater than 2.
Yes.
Up to Z squared is 3.
You also have 1 over H0 squared times Z squared.
No. No, I don't.
Second term.
No. What, here? Yes, but then I'll put that.
No,
No. If you put it here, you have these terms here. Then you have this squared. So you have this 1/2 H0, which we will have to use it here in here. Then you get this Z squared. This is why you get this minus here. Sorry, this you get why you have here minus half Q0 and not no. This is okay. Minus half, not the plus half that you have here. So now I have PL is A0R times 1 plus Z. So finally I have DL is equal 1 over H0 times Z plus 1/2 1 minus Q0 Z squared plus additional terms. What is that? That has a name, actually, this equation. You've heard the name. What? What's the name of this equation? What? No idea? Really? No idea? That's Hubble's one. That's exactly what Hubble did. He measured the distance to galaxies, nearby galaxies. He measured the redshift. What do you get? H.
How do you know
That's
Q?
Right?
Q. You can also
It will be the correction. Right? I mean, this term is linear. Right? This is linear term. And then you have a correction. So you measure it. Right? You measure that it's not going in a straight line. What?
You can use a parabolic fit, not linear.
Yeah. Fit does not have to be linear. Hubble started with a linear fit, obviously. This is, by the way, this is taken from Hubble's paper. It's exactly what you have here. This is the distance. This is the velocity. I don't know if you can see. But the dot here represents galaxies. That's, to the best of my knowledge, this is from Hubble's paper. This is the distance that he could measure. Remember, he managed to know the distance by these, what's called Cephates, these variable stars that were discovered and understood. They are not discovered, but they were understood by Henrietta Leavitt a few years before, about 15 years before him. And he managed to identify these same stars in other galaxies. Thereby he knew he could scale. He had this L, so he had this standard candles. So he knew what is their luminosity. From there he could determine what is the luminosity distance, dA, right? dL, sorry. And the redshift he measured by lines, absorption lines. He identified that these are hydrogen, mainly. And there you go. Cool, isn't it? That's Hubble's law.
In that picture, the dots are measurement.
Dots are measurements. These are
with
galaxies.
with error, measurement error.
I think there are a few. I know that he used 27 galaxies. What did he do about the errors that I don't know?
So how come there's the deviation
How come there's
from
deviation?
the line?
Come on. You can think of so many reasons why there is a deviation. Right? There's a deviation from the distance, there's a deviation from the redshift, there is, remember, he was using the technology he had, that was in 1929, that was nearly 100 years ago. The telescopes that he had, the technology that he had, he used plates, right? Take the photographs. Get these photographic plates. It's completely different technology than what we have today.
So it's a technological problem.
Of course.
So now
But also,
these measures.
Oh, yeah.
It's also not isotropic and not homogeneous.
Right. There are many things here, right? Of course, I could show you. Actually, you don't need me to show you that, right? Just Google in Hubble's law and pictures, and then you'll see today's measurements are done with the Hubble Space Telescope. Of course, that extends to very far away, and then you can measure that, and that's how you measure the deviation, which essentially tells you that there is a cosmological constant. That's essentially exactly. Actually, that's a very fun story, right? Because I know in person Adam Lees got the Nobel Prize for that, and I know the supervisor of Sao Paulo, who shared with him the Nobel Prize for the acceleration for the dark energy accelerating universe. They did it both during their PhDs, which sounds like a completely boring PhD. If somebody would give it to me, I guess I would say no. Because their PhD was to have an accurate measurement of Hubble's constant using Hubble telescope of distant galaxies. That was the project. Like accurate measurement of Hubble's constant, technology in the 1990s, we used the Hubble Space Telescope, and they just look at big sets of data of distant galaxies. Of course, the further away you go, you get to the higher redshifts, and then you can get the redshift we can get. If you know how much Hubble managed to get, where do you see galaxies? Hubble managed to get to redshift of about 9. That's the most distant galaxies. Today, with James Webb, we see galaxies at redshift of 14, which is the further away that there are.
Z is equal to 14.
Yes, Z equal to 14.
So then we must take higher orders of that?
Yes. And this is, of course, what I showed you is the basic. Then you have to take more corrections. So their project, the PhD project, was to have an accurate measurement of H0 using data from Hubble Space Telescope. For me, I have to admit, if somebody would give it to me, it's a PhD project, I would likely say it's too boring for me. But they did, and they did a very good job, an excellent job, and they discovered that the universe is, this doesn't work, doesn't converge, essentially. That they get that they must add some term, which was essentially the acceleration, and that's how they got the Nobel Prize. And the supervisor, by the way, did not get the Nobel Prize, only the student. Think of that when you think of PhD. Okay, so that's Hubble's law. So we can measure this. Right? These are all measurable. Okay. Evolution of the scale factor. Just to erase Friedman's equation. A dot over A squared is 8 pi g over 3 rho minus k over A squared. Given k, there is no problem solving this equation. Well, yeah, I need to know rho, right? But I know what is rho. Right? You said that what? Sorry?
You assume rho is constant time.
How can I assume rho is constant? You're not listening to what I said. What did we say happened this rho? Rho goes as a to the power minus 3, 1 plus omega. And we said that we have rho matter goes as a to the minus 3. Omega is equal to 0. Rho radiation goes as a to the minus 4. Omega is equal to 1/3. Rho vacuum goes as a to the power 0. Omega is equal to minus 4. And again, radiation is really talking about both radiation and relativistic matter. Matter is non-relativistic matter, dust, stars, whatever. And dark energy is we don't really know. So if we look at matter, for example, raw matter time t, right, is what? Raw matter today, T0 times A0 over A to the power 3. So this is rho critical times omega matter times 1 plus z cube. Omega matter is rho matter today over rho critical, and rho critical today is 3h0 squared over 8 pi g.
Is it time t, right?
Rho m at time t.
Z is also time.
In cosmology, Z replaces the time. Rather than tell you 1 billion years ago, I will tell you this, the redshift, that and that. Right? Because it's the same.
If you know it, how are you hold the time?
Well, it doesn't matter. Z is what I measure. Right? So I wouldn't tell you this happens at redshift. I will tell you this happened at time 5 billion years ago. I will tell you I've seen this thing at redshift of whatever. Right? I'm looking at some galaxy. I don't know, I've seen something in that galaxy happening, whatever. And then I will tell you, I don't know what time it happened, so I'll tell you I've seen that at redshift that and that. So that replaces the time. Right? If what it really means, right, and you know that, 1 plus z really means the time where the scale factor A was smaller by 1 or 1 plus c. Now, same for radiation, right? Rho radiation, T is rho r today times A0 over A over 4. So it's rho critical times omega radiation times 1 plus z over 4. And rho vacuum at time t is rho vacuum today. And we further said that omega total is about 1, omega matter is about 0.3, omega radiation today is about minus 4, 8.2 times 10 to the minus 1. These are the measured values. Yeah.
How do we measure them?
Well, essentially, you just have to sum up over all the mass that you have, all the radiation that you have. With radiation, it's easy because most of the largest source of radiation is the cosmic microwave ray, which is very well understood and well measured. There are some additional contributions from light from stars. Okay.
For matter?
What?
Matter.
For matter, I said this is more complicated because that basically asks what is the mass of galaxies, right? Which is something which is much more difficult to tell, especially because of the dark matter, because we don't see all the masses of galaxies. But we have ways of measuring good estimate of measuring the mass of galaxies. And I mentioned the works by Vera Rubin in the 1960s. The new telescope is named after her, which was looking at rotation curves of galaxies and deduced the potential of the gravitational potential, from which an estimate from the knowledge of gravitational potential, of course, will tell you what is the mass of galaxies, and you know what are the densities of galaxies, at least in the local universe. So you have good enough, very detailed maps of the local universe. Okay.
Since the local universe, the universe is not.
Otherwise, all this story, otherwise this fails, and then all this story is not relevant. Okay. The reason why I say local universe is because when we look at if we go too far, then we are looking at the universe as it was in the past. Right? Again, because the time it takes the photons to reach us from distant galaxies to us. So this is no longer relevant to what happens today. It's relevant to what happened in the universe in the past. Okay. So today, obviously, matter dominates over radiation, and omega lambda is about 70%, so it dominates over boson. So today, omega lambda is greater than omega matter, which is much greater than radiation. But obviously, that was not always like that. Which you can clearly see from here. If we go back into the past, go backward in time, higher and higher redshift. Right. This is z equal to 0. Right. This is higher z. Z equal to 10, z equal to 100. Go to z equal to 1000. To converge eventually. This is today. What happened in the past? The distant past. What was the dominant source of radiation, right? So very deep in the past, the universe was dominated by radiation. Then we call it, surprise, surprise, radiation dominated universe.
Or relativistically moving particles.
Or relativistically moving particles, yes. But essentially it's radiation. And then after that, it became dominated by matter. And recently, in cosmological terms, it became dominated by vacuum. So, forget about the vacuum for a second. So there was some time in the past in which the energy densities of matter and radiation were equal. Right? There was some time in the past, right? And we call that equilibration. Okay? So today, omega matter is much greater than omega radiation. But in the past, they were equal. At time T equal T equilibration, which is, A was equal to A equilibration, and omega was equal to omega equilibration. We have that 1 plus Z equilibration, which is A0 over A equilibration, is omega matter over omega R, which is approximately 3600. So at redshift of 3600, universe was equal in radiation and matter in terms of energy.
Omega M,
Yeah.
A0.
What's the problem?
Then you mean the density?
The energy density in radiation. If you go early times mean larger redshift. Right? Early times with larger redshift, then the universe energy was dominated by radiation. Okay? At the redshift of 3600. Above that redshift, it became dominated by matter. Okay? Now, what about the temperature of the universe? How did the temperature evolve to say? What? Yeah, how? What? No.
Assuming
What is the main source of radiation?
Cooling.
Yeah, it's cosmic microwave background, which is a black body. Now, how does the black body evolve as a function of energy, right? Density? To the 4, right? Stefan's law, right? Yeah, Stefan Boltzmann. So Stefan Boltzmann's law. Stefan, I'll be writing this down. Stefan Boltzmann law, right? T to the 4 is proportional to rho r, which is proportional to 1 plus z to the 4, which means that T goes as 1 plus c. What? Stefan Boltzmann's law is no Boltzmann law.
Yes. Why did you choose?
What? The energy density in radiation is mainly cosmic microwave background, which is a black body. So, say the temperature of the cosmic microwave background today, 2.7 degrees Kelvin above the absolute zero. So at equilibration, so T equilibration is equal to T0 today times 1 plus Z equilibration. So this is 2.7 times 3.6 times 10 to the 3, which is about 10 to the 4 degrees Kelvin, or 0.9 electron volt. You all following me? Don't like the looks of the faces.
Temperature of the sun.
No. It's temperature of what? What is that?
All around here.
Very
Yes.
hot.
Ah, you're asking to compare that to the temperature of the sun?
Where?
Yeah, the temperature of the sun is about 6. The surface of the sun is about 6,000 degrees Kelvin. The center of the sun is millions. Okay? So yeah, so the universe back then, the very young universe, did not look at all like the way it looks today. It was very hot. Right? Let's talk about that in a second. But in the meantime, let's first solve Friedmann's equation, which is written here. Right? So, in fact, I'm going to do a simple job, so let's take k equal to 0. So solve Friedmann equation for k equal to 0. Right? So k equal to 0, this is Friedmann's equation. Right? For k equal to 0, I don't care about that. And, okay, well, I know what is rho matter. It's actually written over here. I know what is rho radiation. It's written over here. So just plug it in here, and it's just written here. So rho r, a0 over a to the 4. Just plug it in. It's automatic to solve. So you end up with a of t. So for matter, we have a of t 9 over 4 8 pi g 3 omega matter rho critical a0 q power 1/3 times t to the power 2/3. For radiation, we have a of t is 4 times 8 pi g over 3 omega radiation times rho c for critical times a0 4 to the power 1/4 times t to the power 1/2.
Go back.
Hold on a second. So this is t. This is a of t. We are today. T0 is today. So today, the universe is, let's say, matter-dominated. Right? So A of t goes as t to the power 2/3, roughly.
So
It will be convex.
Right. And when we reach the equilibration, which is here, right? A of z of 3,600 roughly, then it switched to t to the power 1/2.
שנייה מקרים הגזרת
Half t to the 2/3. Right. That's fine. Just plug it in here. Put row, plug it in here. These are the solutions that you solve. You don't need them.
שני הפתרונות וגם פרופורציה שלהם, הנגזרת השנייה היא שלילי. זה כאמור.
בסדר. תור את זה. It's okay. Right. Again, I'm doing something which is very simple, right? I'm just solving for just radiation, just matter. Right? I didn't solve. Of course, we have a combination of all of them, so we need to. The real equation is way more complicated than that. But this will be the asymptotes. This will be here relevant. Of course, the transition is not exactly like that, and there is something. No. But asymptotically, this is the correct line. What about vacuum dominated? So for vacuum dominated, right. So for vacuum dominated, we have rho lambda is lambda over 8 pi g. So the solution, again, plug it in here. This is constant. A dot over A is constant. And we have A of t. In fact, here I did put all the values for all the 3 values of k. So it's hyperbolic sinus of lambda over 3, 1/2 of t. K is -1. The simple exponent plus minus lambda over 3, 1/2 t. K is 0, and it's a cosine hyperbolicus of lambda over 3, 1/2 t, if k is equal to +1. In fact, these are all the same solution, and this has a name. This is called the Sitter universe. You might encounter the name. If lambda is smaller than 0, this is called the anti-de Sitter universe.
You say the center of space is what the
It's all over. The Sitter is all this called the Sitter.
Oh, we said okay, because one geometric could describe it as
Sitter space. Or Sitter universe. These are the technical terms. Yeah.
for the matter radiation parts. Assume that k equals 0. We don't know that. Solution we don't know if k equals 0.
True.
How different will the solution be if k is 1
Solve it.
It's complicated.
Solving. Life is complicated, but it's fun.
How
So we should get here some exponential rise.
How different will the solution be for k equals ±1?
But
How different will the
no, it's not going to be. It's not going to be different
It's going to evolve at the same.
because it's going to. You have a contribution here of 1 over a squared, or 1. It will be a constant contribution here. It's going to be individual. Well, come on. I'm doing the easy things. Difficult ones you do at home. More difficult ones, the exam. That's the way it works. Let's have an exponential. Ex. Now, I left that open. Right? Of course, we said A goes to 0. We said when A goes to 0, the laws of physics fail, so I don't really know what happens. So something happens here, and then here is a place which, what I mentioned before, I just mentioned it, that's called inflation, right? Which is there to explain why the universe looks flat. It also is there to explain something which is even more interesting. How come when we look at distant galaxies, they look isotropic in all directions? Why is that an interesting problem? Because they never had time to communicate with them. Right? Remember, what we see, since the universe has a finite time, then light could travel a finite distance. Right? So different distant regions of the universe have never had time to communicate with themselves, to exchange information. Right? Still, they all look the same to us. But again, why is that?
Why shouldn't it be?
Why should they be? If they never had time to communicate with themselves, right? So they never had time to terminate. We're speaking about. You used to think of thermalization. Right? I mean, the temperature in this room, right? It's quite fixed because molecules had enough time. There were many interactions. They had time to talk to each other, in a way, exchange information, exchange energy, momentum. But different parts of the universe never had the time. They never had this opportunity to exchange information.
You mean, for example, the same temperature? Or
Yes.
In what sense?
Yes, exactly. Why does the cosmic microwave background have the same temperature everywhere? If it never had the opportunity to talk to each other. Right? So maybe the inflation is there to partially explain why maybe sometimes in the very distant past there was a way of communicating, and then there was a huge inflation, so all the expansion was not like that, but inflating, and then it continued the way we see it. Okay, we're running out of time. So that's, by the way, if you've ever seen that, if you look at this is exactly what we're talking about, right? Initially there was this, goes to the power 1/2, then it grows. Another thing that you see here, okay, so the first, now we really don't have time to talk, went far slower than I thought. The next thing is to speak about observational evidence, what we have here. But that actually we can save for Thursday. Maybe it's a good time to stop and ask you if you have any special requests for Thursday, because there is one more subject that I will cover for sure, which is observational evidence. And then we can go in 3 different directions, and you can ask. One direction is to continue on discussing about kosmology, particularly the cosmic microwave background, or alternatively about the thermal history of the universe, and then I'll show you how what we see in the cosmic microwave background, how we can, the connection between particle physics and cosmology. How, for example, from the measurements that we have in cosmology, we know, for example, to limit the number of particles of fermions and bosons in the universe. So that's one option. Or to talk about cosmic microwave background and what we can learn from it, that's another option. Another option is to give you some sort of introduction to gravitational waves, to show you what it is. In a very basic, this is another solution. It's a perturbative solution to Einstein's equation. So we take Einstein's equation, we make a perturbation, it's the weak field limit, with an extra term. So we end up with this h, eta is equal, g is equal eta plus h, and that h we can show that it has some properties which essentially beats gravitational waves. Or what we can do, if you really want, is if there is another subject that you want to review because it's the last lecture before the exam and you feel it will help you, you can do that as well. So I give that as an open question to you. Is there any preference?
Is there any chance we would have another lecture after the semester ends?
A lecture after the semester ends? Am I so popular?
Yeah.
A lecture about what?
Like things we hadn't time to cover.
Look, you can ask for general advice advanced GR. There are many things we did not cover in GR. We did not cover parametric, we did not cover quantum GR, we did not cover cosmology, which is, this is just called introduction to cosmology. We did not talk at all about gravitational waves. I mean, gravitational waves typically would take 2 to 3 weeks to do with the knowledge you have today. I mean, you know, you can do your PhD in GR, right? There's no limits. Yeah.
The connection to particles sounds interesting.
Yeah, it's the most difficult one to understand. Yeah. It requires a little bit of talking about fermions and bosons and some knowledge about
In any case, we did the gravitational waves development similarly to.
I'm not supposed to do international work software. Likes to do that. Fine. Okay. Other requests? So we do some connection to particle physics we can do, and maybe I'll talk a little bit about the CMB. Because all the information there, not all, but there is plenty of information in there, which is hidden. You just need to know how to read it. Okay, so you have a tutorial with Akshay, 12 to 1, so we'll continue, finish with the precession, so at least this will be covered. By the way, I think you're supposed to get write your opinion about this class. Of course, it's anonymous, you know that. If you like it, of course, say it. If you don't like it, you can improve, say it as well. I'll see you on Thursday. If you really, really insist, we can do a lecture next week. But you have to really want it, and you have to tell me that many people will have to plan. There's no problem. But again, I think if you really want, ask Yossi to have a full semester advanced GR course, and then we can cover all the subjects we did not talk about here. There are many fascinating subjects.
It will be a course of advanced relativity next year?
To the best of my knowledge, teaching next year is already set. You can ask Yossi.
Okay.
It's doable in principle. I'll have to find the time to prepare that, because as you can understand, preparing it takes time.
So it's not too late?
You know, it's not too late. The thing is, what I'm more worried about really, I guess everybody here is an undergrad. Undergrad means Torah Rishon. Undergrad is Torah Rishon, graduate is Torah Shlishi. There is no Torah Sheni in the big world. The important thing is in undergrad is that you get firm basis. Not that you know advanced material. I'm way more concerned that you did not see precession than if you don't see gravitational waves. Because if you have a very firm basis, if you understand the concepts of how these things work, you can open a textbook and read about gravitational waves yourself, and you'll understand it. Because you have all the tools that you need to understand what's going on. If you don't have a firm basis, right, then it's a much bigger problem to fit it in, because then there is no point you can go on to discuss about advanced subjects for if your basis is not firm. So that's why I'm not against it. I think it's great. It's great stuff, but it's heavy stuff. It's basically not aimed for undergraduates. It's aimed for this course itself is sort of marginal between undergraduate and graduate studies. I try to take it enough at an undergraduate level. Well, let me see that. Okay, so let's meet on Thursday, and if there is a demand for talking about something more the week after, then come and tell me that, and then we'll see if we can fix that. But it has to be for a group of people, not just a single. Right? Okay, thank you, and see you on Thursday. Another thing, last thing, right? Officially, Thursday is the last time we meet. So really, before the exam. The exam is set for August 4th. This is like 3 weeks from now. If there are gaps in your knowledge, this is the last official time that you can see me. I'm available. I'm in my office, but it's always a good strategy never to wait to the last minute. you have something in the last minute and you might find that I'm not there, I took a holiday, I'm on a travel or whatever. So don't wait until the last minute if you have any questions or things that you don't fully understand. Clarify or make sure that everything is clear in your mind before we go. Yes?
Could you schedule a practice prepare for the test? Or,
I can put last year's exam on what was the webpage.
No, some person.
What?
Show practice for the
Look, questions in the exams essentially are similar to the questions in the exam. Sometimes, and you'll see that, I'm not hiding that, I'm taking a question that appeared in your homework and I put it in the exam. Then, if you did not do it exactly by yourself, then you suddenly realize that it was not a good idea. And if they are not, then they are of the same basic aim. Right? Of course, covering all the subjects that we cover. So in that sense, the homework is the best. I mean, we can do it here, but it will be like solving. I'll give you like an exercise you have to solve. I'll let you solve it on the board if you want. Just get you more stressed. That's the way it works. If you really want to do it, the way it will work, I'll just circulate your question and say, okay, I want to come to the board and solve it. That's the way it works. It always works. Really, if you are doing your homework yourself, you need not worry. I'm not the kind, I don't believe in inventing the new physics during the exam. Exam is not the time for you to discover physics. Exam is the time for you to show that you understood what we talked about during the semester. Right?
Do we have a formula sheet or
Mama?
we
You don't want.
Dat was all.
No, there's no need. I'll tell you, there's really no need. You can bring whatever, it's not going to be helpful for you. Because I'll give you everything you need to know, and things we asked about will not be in any of the
things like precise expression for the given tensor in terms of the affine collection.
That's a great idea.
What?
Great idea, right? I don't expect you to remember that back. Things such as geodesic equation, yes, you need to know. Things such as how to derive the Riemann tensor, yeah, this is not something I asked. We'll discuss that on Thursday. Right?
When the last homework set,
What?
the last homework set.
Okay. Should give it now. Who says it's the last? Okay.
Nobody?
They have solid state lecture and they get credit for just being, so they will watch it later.
Good. I mean, I think it's already uploaded on Moodle as well. It's already uploaded, right? Okay, good. Good. So, I'll just, since we have less time, okay, I'll try to finish it today and maybe take one problem if I have some time. So, what is a rigid body? A body composed of n number of particles, such that the distance between the constituent particles does not change over the time. So I have a mostly not all the solids, but rigid body, it has the definition, nothing changes over the time. So all the two particles which were at the particular distance from the center of mass will remain at the same distance. Then we define what is precession. Like if I have a rigid body which is rotating, so along with the rotation of the body, the axis of rotation also rotates. So if you remember, I had this diagram. Let's say Earth. So this is the axis of rotation. Due to the external torque, or even without the presence of external torque, the axis of rotation also rotates. That's what we call precession of the rigid body. And I look at the syllabus of the analytical mechanics, by the way. So the syllabus mentioned at the end of this all thing, the rigid body dynamics is there in the analytical mechanics syllabus, but there is a bracket in front of whatever is written there, if time permits. So I think that time never permits.
Yes.
That's the case. So this is never included in.
5 years ago, I think. 5 time permitted.
Okay,
Well,
maybe I don't know. So moment of inertia tensor. What we are going to consider, what we already considered, that we have a rigid body made up of the n number of particles, and the particles are situated at the distance Ri from consider center of the mass. So I can write I as okay.
The tensor is calculated once when the particle is, when the body is in some instant, and then we say it is conserved, but
Yes,
not.
not really. I mean, okay, there was going to be some changes, but we are not going to deal with the complicated stuff, so we just ignore that. There's
not really complicated stuff. The tensor, the products of Ri times Rj, the non-diagonal terms.
Yes,
right?
so that's what I'm going to
also
consider. When I'll derive, I'll consider all the terms which are like second derivative, first derivative, or the cross terms. We will simply neglect that.
I'm saying as the body rotates,
Yes,
you're saying, let's say, even taking a diagonal term, right?
yes.
Diagonal moment of inertia tensor.
Mhm.
The components on the diagonal are r squared minus x squared, right? Or something like that. And
Mhm.
as the body rotates, x squared changes because, well, if your coordinates remain fixed,
Yes.
or and so if you're changing at the speed of omega, then x goes as x0 times cosine of omega
Yes.
t.
So why
so-
is that a problem?
So the moment of inertia should change with time.
No, but if you define like the total moment of inertia of a body, like if I have like I, so this is equals to Ixx x component plus y component z component. The total moment of inertia will remain the same. The components will be changing.
Maybe. The components.
Yeah, the components will
change.
definitely can change.
Okay. So I did treat. I know dealing with this classical mechanics. Second year, first year, which is the moment of inertia to be constant. When they derived it, talk about this being some analog to mass, right?
Yeah, kind. Yes, okay. But that was very,
One-dimensional motion.
yeah, kind of a very, I would say, not a physical definition, because there you just define I is mr square. It has something to do with the mass, because like a body is like in motion, and like let's say a truck filled with a lot of concrete or whatever stuff it is moving, and it just somehow try to like stop immediately. What happens?
Can't.
No, I mean, you can, come on, you have brake, you can. But the
Squeeze them.
yeah, exactly. So it's like I don't know. I will not draw the truck actually. So it's like a very I don't have.
Vibration inside.
Yeah. So it's like how do they define inertia in like classical mechanics when they start teaching for the first time? Like if you have a truck, a huge box is loaded on it, so it has some amount of inertia. If I try to stop the truck at one instant of time, the moment the inertia of that huge whatever stuff that is loaded on the truck, it will not immediately stop. It will try to move with the velocity it already had. before the stopping, because I'm stopping the truck, not the stuff that was loaded on it. It had somehow attached to it. So there were, if you can see on the internet, there will be the photographs of the trucks loaded, and the entire first half of the truck will completely get.
But I think what he means that as the object is rotating,
Yes.
and every frame you look at it, all the particles in the object change places.
Yeah.
Except if you're looking at the
That's the frame of the rotating frame.
Yes.
rotating frame. Right.
Yeah, so here we, okay, then when I derive, we do look at from the two frame point of view, like me as an observer from outside, and the, from the frame of the particle, like the co-rotating frame of the particle itself from the rigid body. Okay, so we already, yes, I use angular momentum L as I omega. Then I wrote the component of angular momentum, and then we defined the what is principal axis of rotation, and all the three Euler's angle. If you remember the Euler's angle, I defined T is a vector. Yes, so dl over dt, or dl over dt in inertial frame is dl over dt in co-rotating frame plus L cross omega. Then we wrote the component of it all along all the three direction, and then decided to put this dl by dt, that is the torque acting on the body, to be 0, and describe the free precession. Okay, this was the thing that we did last time. Now what we are going to do is to consider that the body is moving in, means its body is rotating in presence of an external torque, and how does that external torque impact the overall motion of the rigid body itself and the precession of the body, precession of the rotating axis itself. This is all, I think, no, I don't think, it is from the second year of mechanics. There's nothing fancy in here. So this would be very much clear. Only thing is in second year analytical mechanics, or up to what you have studied in the mechanics, they were defining the moment of inertia as a single one body motion, so I equals mr square. You never talked about there is a tensor as well, because it has the component and all, which you can write it in the form of matrix and all those things. Okay, so no more recap. Torque exerted by gravitational potential in non-symmetric object. Torque exerted by gravitational potential on a non-symmetric object. Okay, so here again, we'll what we are going to do is to consider we have a rigid body of m having the n number of particles, which has the masses m1, m2, m3, and we'll write down the potential. So the easy way of writing the potential, the way we write is summation over yes. So G m m I over R I is I. Okay, but here I Okay, so what we are considering in here, a rigid body composed of m point masses particle mi, and these particles are located at the distance ri prime from the center of mass.
Center of mass is not M, right? Not where M is located.
No, the center of mass is located here.
Center of mass is located at M, where M is located. Because the center of mass of the Earth is not located in the Sun, for example.
Rigid body that is a collection located at the distance ri prime from no, so actually it's not located in here. This is the second source of the gravitational potential. So actually it is here. The statement reads that the consider a rigid body that is viewed as a collection of point masses mi located at distance ri prime from the center of mass. So this is the distance. How I can write this as, if you look at it carefully, I can write here, since r square is equals to ri square plus ri prime square minus 2r prime cosine of angle theta. From this geometry I can write this thing. This means that I can write, oops, oh no, did I make any mistake? This is Ri, right? I need Ri. Ri is r square plus my mistake. Okay. I will put it in here. We have V minus of G M I over square root of this term r square plus ri prime square minus 2r r prime cosine of psi G M I. I'm going to take R common from in here. So I have, if I take R1 plus R I prime by R the whole square minus, this is minus in here 2 R prime over Ri cosine of psi.
So there's an expansion in terms of the Jean polynomial.
Yeah. So now we'll use the Legendre polynomial. Same thing. If I have 1 upon square root of 1 plus x square minus 2xt, maybe? No, 1 plus t square we have. Okay, I have defined it. I'll write the way it is written in here. Okay. Legendre polynomial. Right? L-E?
L-E-T.
Oh, thank you. Polynomial. If I have this thing, this is called generating function. How I write this? As like n is 0 to infinity Pn
Tn of x.
Tn. Okay. Now use this and write this thing in here. Okay. Now we can write this equation as v equals to minus gm over r. M is 0 to infinity. Mi Pn of cosine of psi into r prime over r, am I right, raised to n. Okay. Now we are going to assume that R is way too much larger than Ri prime. What does this mean? Yes, but from here that means that this body is at very, very far away compared to the distance from center of mass.
Is it true for the
Yes, we'll see. Yeah, that's what we are going to. Okay, so what we are going to write down is to write down the components of this Lassender's function for up to some order of magnitude which has substantial contributions. Okay, so I will write down in here the components of this, whether it is 1 or 1, yeah. P1 of x is, no, it's x, I think it's x. P2 of x is 1 over 2 3x square minus 1. Good. Okay, so these are the first 3 components of the Lasender polynomial that we wrote. Okay. Then I am going to state one statement which you should be happy with. If you are not, you can go and read the textbook where it is taken from, that is Goldstein. It is very easy, but I'm not going to prove it in here. It's a 2-line statement, but you should have understanding of what I'm going to say. Okay, so what I'm saying in here, by the definition of center of mass, the contribution from n equals to 1 term, which I have written in here, in the equation here, yes,
0.
is 0. Should I write? Okay. The contribution from n equals to 1 term is vanishes 0 instead of vanishes by the definition of center of mass. Okay, so what I am going to do is to only write the second, that is n equals to 2. Okay, good. So let's write it down. X equals to 2, that is going to be, so for n equals to 2, we have gm over 2r cube mi ri prime square 1 minus 3 cosine square psi I, which I can also write as gm over 2r cube mi ri prime square 3 sine square psi I minus 2. Just cos square 1 minus sine square. Put in here, you will get this thing. Okay, good. Now this term in here, which one? This one. So now from the previous definition which I defined in the last class, mi ri prime square sine square psi I is IR. This is the radial component of the moment of inertia tension, the first term. And now the second term, should I write it here? I'm writing it too big. What is that? Okay, I need to reduce my font size. Otherwise, I
way too small. It's hard to see it in the recording. So,
okay. Whereas this component minus of 2, so yeah, so 2 mi ri prime square and summation over I 2 mi ri prime square. Oops. I can write it as a summation over x. It's I mi yi square plus zi square plus mi xi square plus zi square plus summation of I mi x square plus yi square. Everything is in prime coordinate. Okay. Okay, so then let's write down this equation here again. How I can write it as V equals to, therefore we have V equals to minus of Gm. I will remove this term as over R. Now here I am doing the summation, so summation is not included in here. So Gm over R2 RQ. This is minus, I guess this is minus, times 3 times IR minus IXX, right? Yeah, x prime plus I y prime plus I z prime. Good. This is what we call Mach formula. Okay. Okay. X, Y, Z, whatever. Just here. This is just to show that. Okay. Now what we are going to do is to simplify this formula and somehow try to incorporate the Euler's angle to get the precision for the torque, for the rotation in which there is an external torque by external gravitational potential. Okay, so what I can do is to write down the direction cosines. I suppose I have a coordinate system xyz, simple xyz. How do I write the direction cosines? I have r. If I want to write r, I can write, let the angle be alpha, beta and gamma. Okay, with our 3 axes, the angles are alpha, beta and gamma. I can write magnitude maybe, cos sine of alpha the whole square just considering the magnitude of the unit vector in here. That is equals to 1, right? So, I mean, what I am going to do is to write it down in a very simple form. Instead of writing like that, I will write it like this, equals to 1. For my simplistic case, instead of writing the whole stuff. Okay? Happy? Okay. So we have alpha square plus beta square plus gamma square equals to 1. Now what I am going to consider is to let the axis of symmetry is along the EZ axis. That means if you remember from the last time, we have I x prime equals I y prime I, here it is not written, but this is equals to I perpendicular, yes, and I z prime is equals to I parallel. These two are equal, but this is not equals to them. Let's just put down these things in here. So first let's write down the IR first, because IR is IXX, no, I have to write the whole thing, okay. Alpha square plus I y prime beta square plus I z prime gamma square, okay. Use this thing. What I can do is to write I instead of, okay, it's written I x prime alpha square plus beta square plus I z prime gamma square. Alpha plus beta square is 1 minus gamma square. Okay, let's write it down like this. So it will be I x prime plus I z prime minus I x prime gamma square. Here I have used the fact that alpha square plus beta square is 1 minus gamma square. A little bit of manipulation, nothing very. Okay, then let's write down this whole stuff. Okay, let's write, this is the star equation number. Then is V equals to minus of G M over R, that is going to be remaining same, plus G M I parallel minus I perpendicular, 2R cube 3 gamma square minus 1. But 1 by 2 3x square minus 1 is P2 of x. If you remember, I think it's already written there. Why did I wrote again? Okay. So what I'm going to do is, instead of writing this term, I can remove 1 over 2 3 gamma square minus 1, and I can write it as a P2 of gamma. Okay.
You have R gamma and it's almost the same.
Oh no.
Yes.
Oh, no.
Okay.
Is there?
Don't confuse them.
Yeah, no, I'm not going to confuse, but the problem is you people might confuse. Oh, okay, that's a. Yeah, so this is R, this is gamma. Sorry for my writing. So what I'm going to do is, since I know that this is equals to this, I can write this as P2 of gamma. Okay. it was 2 gamma cube 3 gamma square minus 1, but this is equals to this. So I just use that fact in there. Okay. Good. So we did all the mathematical stuff that we needed to, no, not all, but more than half of stuff which we needed to include the gravitational potential. Is there any problem in here? No. Okay. Good.
So again, this is assuming something which has symmetry around the axis, right?
Yes.
Does the Earth have that?
Hmm?
Does the Earth have that?
So I already erased it. So
The Earth is
so the topic name itself is torque exerted by gravitational potential on non-symmetric object.
Yes, but we've written I
But I decide the axis as z axis in here.
Okay, so you're assuming symmetry around the z-axis.
Yes.
Does the Earth have that?
It's
remember the drawings of the Earth and its axis being slanted a bit and it's being licked in this direction, and it's not symmetric in any direction. And just approximating it to the
yes. Okay. So everything comes out at the end to the approximation, because we can include the other more complicated stuff, but we decide like, okay, we have z prime axis, it's symmetric, be happy with that for time being.
Do we get 365 days?
Around we do get, but there are more complicated motions as well, like wobbling and the presence of atmosphere in Earth, molten lava and stuff in the Earth core. That also creates a lot of other what you call extra potentials and extra terms. So you don't get exactly, but somehow you do get. Okay, so we'll now consider the precession of Earth. So I'm going to draw the schematic diagram, which is drawn in the. If you have lambda open, you can look at it there, because I'm not going to draw it very nicely. Z, Y, X. So this is sun. This is theta. This is phi. Cosine inverse of gamma. This is gamma. Okay. Direction to sun. 2 sun of sun. Yeah, 2 sun. And the rotation axis of Earth. Okay. Not that bad. Okay. So what we are going to do is consider the precession of Earth. Earth is subjected to the gravitational potential of Moon and Sun. We know that. But we are going to consider that. Let's that gravitation potential is in the xy plane. Here we have Sun. Okay. Let's consider this is Sun. Okay. It's assumption. Okay. And this is and it makes an angle phi with the x-axis, and the axis of rotation makes an angle theta with the z-axis. Yeah, axis of rotation makes an angle theta with the z-axis.
Where's the Earth? Where's the Earth?
So it's a it's here. Okay, so okay, this is the angle gamma, because this picture it is not really clear, but there is a picture in Goldstein, the book where it is taken from, where the gamma is defined. So now the earth is rotating, so this angle gamma changes with the time. I cannot draw in 3D, I mean we need to visualize it somehow, that because of the rotation this angle gamma
Because of
changes.
the rotation around the axis or because of the precession?
No, because of the rotation.
But the gamma is the angle between the axes.
These two. This is the rotation axis of the earth and the direction of sun. So it is due to precession. It is due to precession, not due to the rotation. It is due to precession, yes. Okay, and we gave this gamma term as, yep. Okay, gamma as sine theta cosine of phi. You need to do little bit of visualization in here. How does this come out to be? Gamma as sine theta cosine of phi. If you want, you can look at some of the nice videos which are on YouTube where it just, I mean, people do show the rotation directly, so there you can really understand how is the rotation happening. But this is the gamma angle that comes out. Here we cannot show it because I'll have to do all sorts of rotation and stuff. Okay, and now what I'm interested in is to get the overall potential, the average potential of the, means the average potential in which the earth is rotating. So in order to take the average potential, what I'm going to do is first I'll put this thing in there, this gamma. I erase that thing, okay, but still let's write it down there. So we have V equals to minus of G m over R plus G m over 2R cube 3 into sine square theta minus 1, if I'm not wrong. Okay. Oh no. G m over 2R cube I parallel minus I perpendicular into 3 sine square theta minus 1. Okay. What did I do in here is to, if you put gamma in there, it is sine square theta cosine square phi. But I took the average of cosine square phi over the angle of precession for the one rotation to be 1 over 2. Did I include that 1 over 2? Yes. Oh, no. That's the bad thing. Yeah, I did not include that 1 over 2. Okay. Since the precession is slow and related to the orbital motion of the Earth, we average it over the complete period of rotation around Sun, and we write this. I mean, you already know that average of cosine over one period, it comes out to be half. That is that half I included in here. That 3 gamma square term was already there, so it's fine.
So you're taking the average of one period of rotation of the Earth
Around the Sun, yes.
Yes. Because the Earth rotates slowly around the Sun.
Yes, because the rotation is very slow. I mean, actually the precession is way slower compared to actual rotation.
Precession meaning change in
The axis of rotation itself.
Okay.
So it's like this is this is rotating. This is the axis of Earth rotating, but this term is also rotating. Okay, I hope this is, so this is rotating already, but along with this rotation, it is also rotating like this, like it's making cone. So this term is fine, right? I just put this gamma in there, 3 gamma square minus 1 term, but and took the average of cosine of phi over one period of rotation of Earth around Sun. Now what I'm going to do is same thing, minus of GMM over R plus, no, why? I can write it in simple form. Minus of Gm over 2RQ I parallel minus I perpendicular into P2 of cos theta.
What happened to the GNN over R?
Oh. This term. Oh, so this is only the second term. This is only the second term. Only second term. Here it is averaged, so I will put an average sign on top. Okay, and I will write it as a V2 instead, just to, so that this is this. I'm just writing on the second term. Okay. Now let's write down the equation of motion.
P2 you have half over also the 1.
Where? This is the one which I wrote here.
But the definition of P2 is half.
So P2 is, I had, okay, let's write down, this term was GM I parallel minus perpendicular and 2RQ into 3 gamma square minus 1. This is the same as this term. This is gamma.
Okay.
Okay. Now, what is the total kinetic energy that I can write? Kinetic energy, I can write E, what is written? E, K, okay, kinetic energy. You know that E is half of I omega square, right? This was the definition of kinetic energy that was used for one dimensional motion, equals to half of I omega square. Now what I have now, since the energy is an additive quantity and I have the rotation along all three directions. So what I am going to do is to write down the moment of inertia and angular velocity along all the three directions. So this will be in here. I can write down Ek is half of I x prime omega x prime square plus of I y prime omega y prime square plus I z prime omega z prime square. So this is the total energy. Okay, and have you ever studied the Euler's angle? No. Did you study Euler's angle anywhere? It's bad. Okay.
If time permits, but time does not permit. And
That is no, actually that. Okay, I don't want to say anything, but the thing is, time will never permit. So I think something has to be removed from beforehand what is being taught to include this, because it is not going to be possible at all with the time.
Secondly, classical mechanics is built very well, and the pacing is done very well.
Euler's angle. So these are the angles introduced by Euler, like really long time ago. I don't know the date, but it is used to describe the rigid body rotation, like the motion in the rigid body with respect to a fixed inertial coordinates. So for now, why we are introducing this term, it will be clear because here we need to work in the two frame of references. One is the lab frame, like I am looking at the rotation, and from the second frame, which is the co-rotating frame of Earth itself. Okay, so for that, in order to get these angular velocities in the rotating frame, I need to use the Euler's angle, because they can be very easily expressed in terms of Euler's angle and their derivatives. So these angular velocity, I am going to somehow use Euler's angle to represent, and then I can use them in this equation and describe the motion. Okay, so how these Euler angles are defined? Okay. So first is defined along the rotation along phi axis, or z axis. Rotation at an angle phi around the z axis. First, rotation at an angle phi around z axis. Everybody has this diagram. If you, I think you can look at that, because I would not dare try to plot it, because I'm very bad at it. This is the very, like, just type the Euler angle on Google, the first thing that comes in is this plot, because this is the very, I would say, traditional way of showing the Euler's angle in here. Okay, so this is the, oops, oh, I rotated by one page. I don't think I'm going to finish, but I have to finish because I don't have any more time. So x prime is x cosine of phi plus y sine of phi. Look at that plot, just rotate by angle and then write down the component of x prime. Just search on Google Euler's angle, whatever comes out is the first thing, and there you can look at it. And then y prime will be same thing, written as minus of x sine of phi plus y cosine of phi. Second is the rotation around y prime, oh sorry, what am I, phi theta. So rotation at an angle theta around nu x prime. And then third is the rotation at angle psi around mu z prime axis. This overall rotation is written as R as B, C, D, where these B, C, D are the matrices of rotation, which I am going to write now. How are these rotations defined? So these rotation matrices also I will write. Remember that why I'm trying to do all this thing is because I'm going to look from the two frame of reference, from the lab frame of reference, me looking at the earth rotating, and then I have to describe the motion of the earth from the co-rotating frame of earth itself. And these rotation matrices are with d prime cosine phi, sin phi, 1, no, 0, 0, 1, 0, 0, minus sine cosine phi, d c is equals to, this is just the notation with the 2 bar on top of it, 1, 0, 0, 0, 0, cosine theta, sine theta, minus sine theta, cosine of theta. B is cosine psi, sine psi, minus sine psi, cosine psi, 0, 0, 1, 0, 0. So these are the 3 rotation matrices, and this is how the rotation is defined. Use this thing, you'll have it in here. Okay. Now, so what we are interested in is to calculating the angular velocity vector in the frame of Earth, that is the co-rotating frame. I'm re-repeating the same thing again and again because this is the region we are using the Euler's angle and why we are defining the Euler's angle and stuff. We are interested in getting this angular velocity in the rotating frame, the co-rotating frame with the Earth. How do I do that? Okay. Since this is an important statement, any general rotation in direction omega can be decomposed, I would say, into 3 rotations. Rotation along phi, rotation along theta, rotation along psi, because these are the 3 angles which I have defined: phi, theta and psi. Okay, so what I'm going to do is to write down omega phi as phi prime, omega psi as psi prime, omega theta, right? Yes, as theta prime. This is just my way of representing that the angular velocity, 3 components. I will represent these things as like in here. Okay, I have 6 more minutes. No, I can take a little extra, right? What else I can do? I mean, like, if I go more faster than this, that is also not good. I hope so. Or you want me to just go?
Go to space.
Unfortunately, I cannot do anything for this recording if it doesn't record after 1. Okay, so now I can erase this as well. Good. Now the phi direction of angular velocity, the phi velocity is omega phi, okay, which is okay, yeah. Phi direction of angular velocity omega phi is parallel to EZ axis. Look at that schematic diagram, there you will see. So, and it is parallel to the Z axis in the lab frame. It is important to note in here that the phi direction of angular velocity
In the earth frame.
in the frame I am looking at.
Okay.
So that I call the lab frame, and the co-rotating frame is the one, yeah, in the lab frame. And therefore its component, what I am going to calculate is it's the component of omega phi in co-rotating frame. Okay. I have omega, what I define is the phi direction of angular velocity. I know that it is in direction parallel to z-axis in the lab frame. Now I want to get the same angular velocity, the omega phi component, in the co-rotating frame, and for that I need to use those definitions in here. So for that, what I need to do is to use this. Oh, what? Oh, it's there. I thought I wrote and I erased. B, C, D. Yes. So I'll use this full rotation along all the three rotations, multiply one after other, and then you will get the component of omega phi prime along x prime direction to be phi dot sine theta sine of psi and omega phi in co-rotating frame. Omega phi prime along y prime is phi dot sine of theta cosine of psi, and omega phi z prime. What? No prime in here. This is not the prime coordinate. This is the prime everywhere. Yes. Component of omega phi along all the three directions in the co-rotating frame is phi dot cosine of theta. Same I will do for the theta direction. Same thing, I have omega theta, which is along the x prime axis. The direction of angular velocity omega theta coincide with x axis. So therefore its component I will write down in the co-rotating frame. It's a okay. So this is in co-rotating frame, the phi component, phi direction. Now theta direction. I have omega theta x prime, which is equals to theta dot